The focus of tonight's lecture is the magnetic universe. Magnetic fields pervade space. All of outer space is threaded by magnetic fields. And if you thought that magnetism was maybe a rather eclectic, perhaps even irrelevant part of physics, then you'll find out in this evening's lecture that that is simply not the case. Magnetism is critically important, not just for the preservation of life on Earth, but as the explanation for some of the exotic phenomena that we see in outer space. Things behave very differently in the presence of a magnetic field, differently from what we might first expect. So let's begin with a familiar manifestation of how an everyday object can interact with a magnetic field. The compass, of course, which we now understand responds to Earth's magnetic field, was critically important for developing navigation, for being able to navigate ships to a particular newfound land and back again. But magnetism should not be regarded as man-made, some kind of unusual manufactured artifact. Far from it. Magnetism is absolutely naturally occurring. Indeed, Thales of Miletus discovered in the 6th century before Christ that certain minerals, this one particularly known as lodestone, had highly magnetic properties. And if it came together with something that was ferromagnetic, for example, a spanner made out of iron, which possibly wasn't around in the 6th century BCE, there would be an interaction. Indeed, the lodestone would somehow keep an invisible grip on whatever ferromagnetic object was to hand, and it wouldn't fall to the ground under gravity as it would do in the absence of any magnetic field interaction. So lodestone, this mineral that's in the rocky type substance in that human hand there, is very much naturally occurring. But bar magnets are, of course, something we're perhaps a bit more familiar with. I'm going to show a photograph now of what happens if you take a bar magnet and you put a sheet of white card on top and then you sprinkle some iron filings on top. Turns out that repeatably, every single time, you get this beautiful pattern. If that is, you keep the bar magnet still and safely underneath the white card, which has all the iron filings on top of it. Underneath this sheet of white card is a bar magnet with a north pole, which is over on the left, and a south pole, which is over on the right. And it's this, underneath the sheet of white card, that gives rise to this beautiful structure, this beautiful distribution of the iron filings. Sometimes you need to tap the white card a little bit to get the iron filings to respond to their magnetic environment. But you can see there's something of a north-south divide in the distribution of the iron filings. They're in very specific locations and they seem to follow very specific shapes of lines. So let's look further at this bar magnet. What happens, for example, if we chop it in half? If you do that, and you do actually need something a little bit more robust than just a pair of kitchen scissors, you end up with 2 bar magnets. And the north-south orientation is the same for each and the same as the original bar magnet. So how do these half bar magnets interact with one another? Let's imagine that we keep the original set with the south and the north in the middle together, but we reverse in a second experiment, we reverse the right-hand magnet so that south is closer to the other south pole, and we do a similar kind of experiment where we have the north poles together. What happens next? Well, the like poles will experience a force of attraction, and the similar poles will repel one another, regardless of whether you're talking about the south-south example or the north-north example. They will move. The bar magnets will shift in response to those forces of either attraction or of repulsion. This is completely repeatable, happens every single time with a bar magnet. So what about the magnetic field lines that emanate from a bar magnet, manifested by the distribution of the iron filings on the white card? Well, the very idea of magnetic field lines is a conceptualization of what's going on with the magnetic field. Strictly speaking, there's no such thing as lines of magnetic field at all. But it is helpful to talk in terms of that picture language because it reminds us that there is a directionality to the distribution of magnetic field lines, which will make a difference to the way nearby matter interacts with it. And that will become really quite important later on in the talk. But before it does, I want to talk to you about how a charged particle, such as an electron, will interact in the presence of magnetic field lines. And that interaction will be very different according to the relative direction with which the electron is moving with respect to a given magnetic field line and the orientation of that magnetic field line. Let's take a couple of extreme examples. So whereas with gravity, we understand that our intuition is very well developed. We have an apple, we let go of it, it drops to the ground. Completely repeatable, happens every time. What about the direction with which a charged particle, such as an electron, will move with respect to magnetic field lines? Now, another big conceptualization here, the electron is represented as that pink circle. And if the electron appears moving from left to right across the screen and it's exactly parallel to the local direction of the magnetic field lines, well, it just moves across, left to right. If and only if it is parallel to the local direction of the magnetic field lines. An electron moving parallel to magnetic field lines will continue to move parallel. It won't respond at all to the presence of the magnetic field, assuming they're exactly parallel. However, it's a little bit different if the electron is moving at a different angle with respect to the magnetic field lines. Let's imagine that the electron is moving exactly perpendicular to the magnetic field lines when it appears in the middle of our experiment. If that happens, the electron will just trace circles around the magnetic field line, just going round and round and round. Now, if you have some intermediate angle between perfectly parallel and perpendicular, which gives you the circular motion and the straight parallel motion irrespectively, then you trace out a helical path, much like the grey line is illustrated here. You will get that every single time, that helical path for an electron moving at an arbitrary angle with respect to magnetic field lines. When this happens, something remarkable takes place. And that remarkable thing is that the electron, or whatever charged particle we're talking about, will emit light. And that happens because when a charged particle is forced to go into some kind of circular orbit, whether we're talking about a perfect circle or whether we're talking about a helical path, it will be undergoing acceleration. And it turns out, because of quantum mechanics, that you can't have that kind of acceleration without simultaneously emitting a photon, in a way that the direction of the photon also knows exactly about the direction of the electron and of the magnetic field lines. This works out in a very detailed way. It's important to realise that what I've just said has been very well established over the past well over a century now, thanks to the work of the Scottish physicist James Clerk Maxwell. He demonstrated that light is comprised of a wave in electric field and a wave in magnetic field. That is what comprises a photon. It travels at the speed of light, and the speed of light is a very special number in the universe. It's defined simply by the magnetic properties of the universe and the electrical properties of the universe. And I went into this aspect in a little more detail in my very first Gresham lecture, which was entitled Faster Than Light, ? So if you're not too familiar with this, I refer you to that lecture. But back to today's story. If you have interesting magnetic field structures, and by interesting, I don't just mean parallel, but if you have interesting magnetic field structures, then you get remarkable patterns in the distribution of light if you've got charged particles rocking up, rattling around, following helical paths around your interesting magnetic field structure. Can we see this in the night sky? Well, we absolutely can. And here is such an example of the aurorae, which we see if you go to northern latitudes, in which case they're often called the northern lights, or if you go closer to the South Pole, in which case they're called the southern lights, of course. You see absolutely remarkable and beautiful structures if it's dark enough so that light from the sun doesn't swamp out these beautiful structures. Whether it's green or whether it's pink depends very much on the nature of the charged particles that suddenly rock up on Earth's magnetic field, whether you've got helium or whether you've got oxygen, or whether you've got something a little bit more unusual. That determines the colour, but the distribution, the shapes that you see in space, depend on the clouds of charged particles that rock up and the magnetic field structure of planet Earth itself. Now, this is a cartoon representation of the kind of magnetic field that we believe to emanate from within planet Earth. And you can see close to the North Magnetic Pole and the South Magnetic Pole, you get a bunching of these magnetic field lines. And that's why you see the aurorae associated with closer, you see it closer to the North Pole or closer to the South Pole. It's because you've got a much greater concentration of magnetic field lines, a much stronger magnetic field strength. And so that's why it's much easier to see the aurorae in or nearer to those polar regions. Besides being really very stunningly beautiful, planet Earth's magnetic field is significant and important for the survival of life itself. Planet Earth's magnetic field doesn't just give us the decorative aurorae in the night sky. Our planet's magnetic field protects us, and it stops planet Earth from being an even more dangerous place on which to try and live. Because the very fact that those charged particles, which come from usually the sun belches and erupts, and in something that we call the solar wind, blasts charged particles in the direction of all the planets in the solar system. Those charged particles from the sun that arrive on Earth start following helical paths around the magnetic field lines of Earth. We see the beautiful patterns in the night sky, but in the meantime, those charged particles are trapped in their helical orbits, their helical paths, and so they don't actually usually end up penetrating our human bodies. and causing mutations and doing damage when that happens. It is a wonderful thing for the survival of the human race that planet Earth has a magnetosphere. Earth's magnetic fields that form the magnetosphere keep us safe from high doses of radiation poisoning that would otherwise come from the solar wind that's ejected from our nearest star. In contrast, planet Mars has no magnetic PPE. PPE, of course, standing for planetary protective equipment. Here's an image of planet Mars that I took from my back garden in the 2 Octobers ago to try and capture its rotation, which you can just about see there. Now, my back garden in Oxford is a distance of about 60 million kilometres from planet Mars. But of course, you get a much closer view of a planet if you're much nearer to your subject. And so last year, in fact, NASA's Perseverance rover touched down on the surface of planet Mars in order to explore it rather more thoroughly. This was a very exciting advance in terms of the engineering prowess that got it there successfully. It's very exciting in terms of being able to explore another celestial body. It was crucially important, it is crucially important for astrobiology research, searching for signs of ancient microbial life. It's exciting because we can learn about the planet's geology and past climate. But it's really important to realise, however exciting it is to think of flying over to Mars, rocking up there and establishing a human colony, it's important not to be naive about how dangerous that would be. Mars is hostile for human life because we would get the full radiative poisoning force of the solar wind. There's a lack of evidence of any strong magnetic field on Mars, and it would be really dangerous to think of living there. The magnetic field of planet Earth is one reason why this planet belongs to what we call the habitable zone. But more of that in the final lecture of this series later in the year. So, the magnetic fields that give the aurorae are the same magnetic fields that are our PPE. There are no aurorae, no comparable aurorae on Mars. Well, that's a little bit about magnetic fields belonging to planets, but now let's look at the origin of the solar wind, the sun itself. So, back in August of 2017, I was watching the total solar eclipse from the vantage point of Idaho in the United States of America. And of course, the main action was the fact that the sun was increasingly being eaten by the moon traversing in front of it. But what you may just be able to make out, there's not quite enough contrast perhaps to see this, is that within that green circle, there are black, blotchy regions. Now, this was not dust on the sensor of my camera, I can assure you. But it absolutely was dark blotches on the sun itself. Now, in 2017, the sun wasn't particularly active. And so that's why only a few little blotches, little sunspots, were detectable at this time. However, back in 2003, my colleague Stephen Lee in Australia was observing the sun at a time when it was much more active than in 2017. And I'm sure you can see very, very clearly indeed the dark, very contrasty sunspots that were observable in the sun at this time of high solar activity. I'm just going to zoom in the green box so that perhaps you can see a little bit more clearly. Right at the centre of each blotch, you see an extra dark region. And that's because something quite special is going on with the magnetic fields. Really, really strong bunches of magnetic fields are coming out of these sunspots. We'll see that in a moment. And where you have magnetic field lines threading through the plasma of the sun, of the star itself, that inhibits the motion, the convective motion within the sun. And so you can't redistribute the thermal energy within the sun. And so that plasma, counterintuitively, actually becomes a bit cooler, it's not that cold, and is seen as being darker. Here are some more sunspots that were seen in the sun in 2011. The sun wasn't quite so active then, but indeed this image, also by my colleague Steve Lee, was taken from light that only permits light in a very, very narrow filter, a filter corresponding to where hydrogen predominantly emits light. And you can perhaps see, if I zoom in again, there's a tendril coming out of that sunspot. Well, what's going on, and how do magnetic fields connect up with sunspots? In fact, if you zoom in, and to do this, we aren't talking about a telescope in a back garden, we're talking about a satellite that's purpose-built to closely inspect the surface of the sun, you can see streaks and indeed ropes of emission coming out. So these are images of sunspots from NASA's TRACE satellite. And you can see big loops of magnetic field lines coming out. As I've said, the presence of a concentration of magnetic field lines hinders convection within the sun. And so that inhibits, convection normally brings hot plasma from the interior of the sun to the surface. But the magnetic fields put the brakes on that. They really put a stop to it. And so you do get cooler plasma in the vicinity of these sunspots if you're looking at optical light, as I showed you in those earlier images. If we take a more wide-angle view now of the sun, again from the TRACE satellite, you can see that the sun is a place of tremendous activity. So the TRACE satellite is NASA's heliophysics and solar observatory. It was precisely designed to investigate the link between the solar plasma itself and the amazing coronal loops that tell us about the magnetic field structure. Now, the key thing to realise is that these coronal loops store huge amounts of magnetic energy. When they touch, you get a short circuit, and this gives you something of a big bang. Not the original Big Bang, but still pretty serious bang. These coronal loops will short circuit one another, and they will set off explosions and solar flares. Solar flares being what launches the solar wind, which can be in a very impulsive way. Sometimes these events are called solar storms. And this happened at a particularly vulnerable time in December 2006. It was a particularly vulnerable time because these two astronauts, Robert Curbeam and Krista Fuglesang, were doing a spacewalk at the time. They were outside of the ISS, the International Space Station. Moments earlier, from mission control, there was warning that a big solar flare had erupted on the sun over an area of about 10 planet Earths. It was a major solar flare. And so they were told to race back into the ISS with moments to spare, because of course they were in a much weaker region of Earth's magnetic field. They were much more vulnerable to the radiation coming from the sun. If they hadn't got back into the ISS in time, they would have either had become very sick with radiation poisoning, if not actually dead. So much like for those of us living in the UK, last Friday we were told to get indoors and stay indoors because of Storm Eunice. Back in December 2006, they were told to get indoors, where indoors for them was the ISS. Bit like getting inside because of Storm Eunice, only, I imagine, rather scarier. Robert Curbeam, the astronaut on the left, they're now both retired as astronauts, but Robert Curbeam now works in the safety office for NASA. I'm sure he has a particularly unusual perspective on safety. So we've talked a little bit about how charged particles respond in the presence of magnetic fields. But I want you to know that if you have charged particles which are moving, that movement gives rise to a magnetic field. And the details of the cause and effect processes between moving current, which is moving charged particles, and consequent magnetic field lines, or indeed varying magnetic field lines giving rise to particular behaviour of charged particles, is all described in a set of equations known as Maxwell's equations, the same James Clerk Maxwell that I mentioned to you earlier in the context of light. I won't show you those equations tonight because not everyone likes equations, but for people who do like equations, these are particularly beautiful ones. Maxwell's equations, you might like to look them up later. But it's important to realise that electromagnetism, encapsulating the behaviour of charged particles and the consequent behaviour in magnetic fields and vice versa, is a thing. It's not just a thing here on Earth, it's a thing in the plasma of the sun. It's a thing in plasma all across the universe. Now, if you take magnetic field lines and then you just add motion of the bulk of the plasma forming the star, then that can twist up the magnetic field lines and alter the magnetic field structure you thought you had to begin with. So even if you start with magnetic field lines that just go from the South Pole to the North Pole, if you've got the equatorial belly of the sun rotating a bit faster than plasma is rotating closer to the poles of the sun, you're going to be rotating the magnetic fields which are frozen into that plasma. And you're going to end up with plasma that goes round in loops parallel to the equator. And that's going to give you very different behaviour. Depending on the details of the starting point and the turbulence of the plasma on the surface of the sun, you will end up by creating loops, which, being highly energised, want to expand. And when they start to expand, they might expand into one another, giving those short circuits I mentioned, or they may just break, either way launching the solar wind, endangering the lives of astronauts, but not really endangering the lives of us here on Earth, thanks to the magnetic field that we have here on planet Earth. So magnetic fields are significant in terms of life on planet Earth, and they are significant in terms of the behaviour of stars. I want to just very briefly take you through a timeline of magnetic revolutions. I think you can make the case for saying that magnetism and our understanding of magnetism have had considerable geopolitical influence in human history. And it really began in, although the discovery of magnetic minerals like lodestone took place back in the 6th century BCE, it was really the 10th or 11th century that the magnetic compass was invented. This took place in China, and the significance, of course, of a magnetic compass is that you could navigate. The minute people could navigate, then it meant it was possible to establish colonies, because you could navigate across the ocean, you could navigate back again, and so on. Around the time that Gresham College was formed, William Gilbert was doing lots of experiments with lodestone and investigating the different phenomena that you could get from that. And he wrote a bestseller, seriously, called De Magnete. And this truly was a bestseller, and it influenced a lot of the thinking of physicists at the time. A century and a half later, the horseshoe magnet, a very strong permanent magnet, was invented. A couple of centuries ago, Ørsted discovered that magnetic fields emanated from current-carrying wire. In other words, wires that had charged particles, current, moving along them. Just the following year, Michael Faraday discovered electromagnetic induction, the idea that you could reverse the consequences of changing current in the presence of a magnetic field or vice versa. That led to the first electric motor, and we all know where that led to, cars all over the roads. A few years later, the first electromagnet was constructed. So this is not something that was a permanent magnet, like a horseshoe magnet or a bar magnet. This was something that was controllable via electricity, the movement of charged particles. It was in 1864 that James Clerk Maxwell, the Scottish physicist I mentioned earlier, formulated his famous equations. Then later came transformers and AC power, alternating current power, the kind that flows through our homes today. But it was only just over a century and a quarter ago that the electron was discovered. It must have been astonishing to have been uncovering all these electromagnetic properties without really having any idea that electrons were a thing. Must have been remarkable. It was only a century and a decade ago that the solar magnetic field was discovered. And that came via spectroscopy. The fact that if you try and do spectroscopy on certain emission lines arising from certain elements in the solar corona, the lines would split in a way that they simply didn't if you had no magnetic field. So that's how recent our understanding of the solar magnetic field is. Quantum mechanics was what explained the phenomenon of magnetism from ferromagnets, magnetism in iron spanners. That, too, was really very recent. Magnetic resonance, which is the crucial ingredient in MRI machines that help diagnose problems in our bodies in hospitals, again, not quite a century old. And then, as recently as the 1960s, magnetic recording was made possible. The recording of data from scientific measurement, from satellite data on tapes became possible. And of course, that propelled the information revolution. Spin electronics is only 3 decades old. Without spin electronics, hard disks wouldn't be a thing. Laptops wouldn't be doing the projection of slides. So magnetism has had an astonishing history. And if you're interested in how our understanding, humanity's understanding of magnetism has shaped the geopolitical world, then I refer you to the Oxford University Press's very short introduction to magnetism, which happens to be written by my husband. End of plug. Let's go back to stars, a bit like our sun, but stars that have even stronger magnetic fields. So if you take a star that's more massive than our sun, but got lots of magnetic fields threading it, because of the motion of its plasma, sometimes with an internal dynamo that whips up and enhances and amplifies the magnetic fields coming from it, and then imagine that that star has used up all its nuclear fuel, so it can't keep the star undergoing nuclear fusion, collapse soon follows in in a process called a supernova explosion. A big shell is blown off, but the bit in the middle collapses to become a compact object. And depending on the mass of the original star, it can either become a neutron star or a black hole, something I've addressed in lectures in my first year. Let's just consider that the original star had a mass between, say, 10 and 25 times the mass of our Sun, and then it undergoes collapse to a compact object because of a supernova explosion. The resulting neutron star will be something like 20 kilometres across. Big by the standards of the lecture theatre that we're in this evening, but bijou in comparison with the radius of the original star. We're talking about a collapse from the original star down to the compact object, the neutron star, by a factor of tens of thousands at least. If you start compressing and collapsing a star into just 20 kilometres across, into the ultra-dense matter that comprises a compact object like a neutron star, the magnetic field strengths become absolutely huge. You're squashing them all together. Magnetic flux is a conserved quantity. Magnetic energy doesn't just disappear because the plasma squashes down into a neutron star. And so you can end up with extremely strong magnetic field strengths for such neutron stars. The magnetic field strengths can exceed the magnetic field strength in our Sun, which gives rise to all those amazing coronal loops and gives a scary time to astronauts, by a factor of 10 to the power 15. That's a 1 and 15 zeros. Hugely strong magnetic fields. When you have such strong magnetic fields threading a neutron star, you have something that we call, it's obviously a magnetized star. When you compress it, you end up with something called a magnetar. The word is, of course, a contraction of magnetized star. But it's important to realise we're talking about extremely magnetized stars. So, how strong are these magnetic fields? In units of Tesla, which I'll calibrate for you in a couple of slides' time, the magnetic field strengths are about 10 to the power of 12 Tesla, a million Tesla. Hold that number for a moment and we'll calibrate it in a moment. It's huge, by the way, but I'll demonstrate just how huge in just a moment. But I want you to just think about the fact you've got this huge magnetic field and it's frozen into this ultra-dense, compact form of matter known as a neutron star. What happens when you get seismic activity within that neutron star? Well, it's pretty dramatic. The resulting blast that can happen when you abruptly shear or attempt to shear such magnetic field strengths dumps a huge amount of energy into the surrounding space in a mere 1/10 of 1 second. And the amount of energy that seismic activity in a highly magnetized neutron star, the amount of energy that's dumped is in that 1/10 of a second is as much as the energy as the Sun emits in 150,000 years. Kind of energies we're talking about are just huge, easily, trivially measurable on Earth in all sorts of different wavebands, principally X-rays and gamma rays, the most energetic wavebands. We see huge flares in those wavebands from seismic activity in highly magnetized neutron stars, in these magnetars. There's another type of magnetized neutron star, which is known as a pulsar. And these are still very highly magnetized, not quite such high magnetic fields as in the magnetars. Their magnetic field strengths are a bit more like 10 to the power of 10 or 10 to the power of 11 Tesla. Famously, pulsars were discovered by Jocelyn Bell Burnell. This is her pictured in 1967, the year that she made the discovery. Jocelyn confounded expectations and searched her data with exquisite thoroughness. She didn't know a priori she was looking for a new phenomenon. She subsequently refers to the signal that she saw at the time, which opened up the entire field of neutron stars, as scruff. That's what it looked like, a bit of scruff in the data. Well, she made the discovery, and she's now a professorial fellow at Mansfield College in Oxford. But her tenacity at that young age led to a discovery that revolutionised a lot of relativistic astrophysics. But I promised you I'd try and calibrate for you the different magnetic field strengths that we've been talking about. So the most extreme magnetic field strengths we know about in the universe at present, we might discover something new in the coming years, but at present, the most strong and extreme magnetic fields we know about are in the magnetars. Their magnetic field strengths are something like 10 to the power of 12, a million Tesla. For those of you who are thinking, come on, tell me what a Tesla is, let me try and calibrate it for you. If anyone here has ever had an MRI image done of a particular limb or part of their body to investigate a problem, the MRI scanner that you will have been put inside for that diagnostic imaging will either have been a 1.5 Tesla superconducting magnet or a 3 Tesla one. Now, for the purposes of today's lecture, 3 is equal to 1. So the magnetic field in a superconducting magnet that you have in an MRI scanner in a hospital, that's about a Tesla. So a million times that is what you have in a magnetar. Slightly less than that, 10 to the 9 or 10 to the 10 or maybe 10 to the 11 Tesla is what you have in a neutron star or a pulsar, depending on what their progeny, what the original magnetic field was in the star that ultimately gave rise to that neutron star. At the opposite end of the scale, we have the magnetic field strengths that are going on in the human heart and in the human brain. Now, while MRI scanners are perfectly safe, it would not be safe to go anywhere near a magnetar. A magnetic field strength of 10 to the 12 Tesla near our human brains and our hearts would stuff them up entirely, because that magnetic field strength would be so strong that the atoms and molecules that comprise our hearts and our brains and the rest of our bodies would be so distorted, we'd be stuffed. People often fixate on the spaghettification that is postulated to happen in the vicinity of a black hole. But trust me, what would happen to the atoms and molecules in our human bodies in the vicinity of a magnetar or a pulsar, you just don't want to go there. Please trust me on that. Well, let's go back to the presence of, the behaviour of, charged particles in the presence of magnetic fields. And let's go back to outer space. So I'm going to talk now about something called synchrotron radiation. This picks up on the idea that if you have a charged particle moving at an angle with respect to a magnetic field line, pictured by the black line going across the slide there, it will, as I said earlier, follow a helical path. And as it does so, it will emit photons, will give rise to light. What's special about synchrotron radiation is that if that charged particle has got so much energy, it's moving relativistically, and by relativistically I mean moving at a speed that's comparable with the speed of light, you get very remarkable radiation indeed. It's completely different if the electron is just ambling around at normal speeds. But if the electron is whizzing round at speeds comparable with the speed of light itself, you get extremely energetic radiation, even if the magnetic field strength is still relatively low. And by relatively low, I mean only 10 or 100,000 times higher than the magnetic field in our human hearts and in our human brains. If you do have sufficiently energetic, sufficiently rapidly moving charged particles like electrons, then that gives rise to these very beautiful radio structures that we see, or at least that radio telescopes see. We're not sensitive to these structures with our human eyes at all, but telescopes that are sensitive to radio wavelengths absolutely can detect these with ease. This is a beautiful radio image of the radio galaxy Centaurus A, imaged by my friends Ilana Feehan, Tim Cornwell and Ron Eakers, with the Australia Telescope compact array shown in the foreground there. That's an optical image of those telescopes. And these balloons of charged particles whizzing around in helical paths along the different magnetic field lines that pervade these balloons that had their origin in plasma ejected from nearby the black hole that's at the very centre of Centaurus A, then it is marvellous to behold these structures. It's just astonishing to think of how they can balloon up to the size that they are. The extent of this is comparable with about 1 million light years. In other words, if you've got a ray of light travelling from one end to the other, even travelling at the very rapid speed that is the speed of light, it would take you 1 million years. These structures are huge, but such are the energies that we're talking about, even in the presence of relatively very low magnetic fields, still quite a bit stronger than the magnetic fields in our hearts and our brains. You see these amazing balloon structures. This is Fornax A, shown us an image of radio wavelengths that are about 20 centimetres long. This was imaged with the Very Large Array radio telescope in New Mexico in the USA. Only about a third of the size of Centaurus A that I showed you in the previous image. It's actually rather good fun to try and image different radio phenomena in space at very low radio frequencies, at very long wavelengths. And I've done this quite a bit. It's really good fun using the Very Large Array radio telescope. Now, the images that I'm showing you here are contour images. So where you see them bunched together, that tells you you've got a very dramatic change in how bright the radio distribution is. And if you just for a moment compare these two contour images, the top one is taken at a wavelength of 4 meters, so pretty much half the span of this lecture theatre here, half the width. Whereas the image below is a wavelength of only about 1 meter. What you may notice and just be able to discern is spurs in the contour levels in the top low frequency long wavelength image, for which there is no evidence in the slightly higher frequency, slightly shorter wavelength image. It's really good fun to image these things. This is Perseus A, by the way, another famous local radio galaxy. It's really good fun to observe these unless you're in a state of high solar activity. If you're near solar maximum and you try observing at these very long wavelengths, and then the sun starts emitting a big impulsive solar flare, that really stuffs up imaging at these long radio wavelengths. So I have struggled with that a little bit. It's another reason, beautiful though the aurorae are, they're dangerous for astronauts, as I said, and they're inconvenient when you're doing long wavelength radio astronomy. But despite that, with such images, if you combine them with images at X-ray wavelengths, then you start to see beautiful interactions going on. So on this right image here, in the colour scale, corresponding to where those spurs are in emission, you can see they're feeding holes, evacuated regions in the underlying X-ray emission shown in the yellow colour scale. So these spurs previously inflated bubbles which have now cooled. And so the combination of investigating the behaviour of magnetised plasma with radio imaging at different wavelengths, particularly long wavelength radio imaging, together with X-ray imaging, tells us a lot about the evolving nature of this magnetised plasma. Well, radio imaging, particularly long wavelength, low frequency radio imaging, is really the flavour of the month in astronomy. And one of the new so-called next generation radio telescopes is one located in the Karoo, pictured here, in the northern part of South Africa, known as Meerkat. Meerkat consists of 64 antennas, each one 13.5 metres in diameter, so you would struggle to fit one in this lecture theatre. You certainly wouldn't get it through the door. So this next generation radio telescope, inaugurated in 2018, is starting to yield some fantastic data. And what I'm going to show you now is a new image of the galactic centre that was publicly released only a month ago. It was published in the Astrophysical Journal, which is one of the premier journals where new scientific data, new scientific results are published. It was also published in the New York Times, which is where I've taken this image from. You probably can't read the small subtitle there, but the subtext, the subtitle is out there. So this is an image of just the very central few degrees of the galactic plane in the Milky Way. And that yellow bit in the middle is the brightest part. That's the location of Sagittarius A star, which is the location of a black hole whose mass is 4 million times the mass of our sun. This particular image is about 3.5 degrees on the sky by 2.5 degrees. And it was made by using a lot of telescope time with Meerkat. Meerkat successively observed this region of sky scanning across in a mosaic using over 200 hours of telescope time. It yielded something like 70 terabytes of data. This image is only about 800 megabytes, so that's quite a compression. It took 40 days to process the data on 2 supercomputers in Cape Town. And this is a truly remarkable image. I'm going to zoom in on different features within the image. But I just want to introduce you to 2 of the team that were involved in creating this beautiful structure. One of them is my friend and colleague in Oxford, Ian Hayward, and another is Isabella Ramallah, who's at Rhodes University studying for her PhD on this beautiful data. What a PhD topic to be studying, the centre of our galaxy. Well, if I now zoom in on that central region, then you can see really very clearly these distinct linear features which seem to just go across some of the brighter features. That's Sag A star down there, looking very bright in its own little bubble. Also seen in this image are spherical, or at least circular in projection, presumed to be spherical bubbles in radio emission. Again, the whole sort of streaky thing is seen with that thing on the left seemingly blasting away at some high speed or other. Well, these circular, presumably spherical regions are believed to be bubbles, blast waves, shock waves generated by supernova explosions. When a supernova explodes, you get a massive, overpressured blast wave of plasma, so overpressured it blasts into space, and with time you see that blast wave get bigger and bigger and bigger. Over the course of about 5 years, half a decade, you see these bubbles get bigger and bigger and bigger. By the time you get to the right-hand side, the supernova remnant is now about 1 light month in extent, meaning it would take light a month to travel from one side across to the other side. Some of the bubbles seen in that new data are absolutely astonishingly circular, as though they've expanded into very uniform and pristine conditions, which is astonishing given the violent activity that's implied by some of the images I've just been showing you. These linear streaks that are seen here, the authors have catalogued into a whole great big collection of these linear streaks. Each of them is quite a few light years in extent, and their magnetic properties are truly astonishing. The kind of, let me skip to this slide, the kind of magnetic field strengths that we're talking about for these streaked linear regions is about 1% of the magnetic field strength in an MRI scanner, in a superconducting magnet that you have in a hospital MRI scanner. So by astronomical standards, leaving aside magnetars, these are quite significant magnetic field strengths. What's their origin? Dunno. It's completely unknown at present why you should have these one-dimensional magnetized ropes in space, seemingly perpendicular to the plane of our galaxy. But for sure, this is one of many discoveries that will come from the next generation radio telescopes, such as Meerkat. There's absolutely no doubt that investigating the magnetic universe is a very rich and exciting aspect of the universe for us to study. Thank you very much indeed.
So the first question is the Earth's magnetic field growing or waning? And if it is one or the other, do we know why? If it's static, do we know why? Tell us.
So one of the reasons why we think we have a magnetic field arising from the centre of planet Earth is because of the nature of Earth's core. It's molten iron, amongst other things. There are other minerals. But molten iron, meaning liquid iron, means you have charged metal, liquid metal, moving around. And as I indicated earlier, that gives you a consequent magnetic field structure, somewhat resemblant of the magnetic field lines that emanate from a bar magnet. Now, is Earth's magnetic field changing, is the question, or is it static? To take the second question first, no, it's not static, it's changing. It's always changed. Excitingly, or maybe I mean worryingly, Earth's magnetic field has flipped. South was previously north, north was previously south, and it's going to do that again. In fact, it's overdue for doing that. Now, exactly why that happens isn't fully understood, but it's some kind of very grandiose phase transition to do with the internal nature of Earth's core. When it happens, it is going to be quite disruptive.
Hi, thank you for the lecture. Super interesting. You know the right-hand rule? So I can find everything explaining what the right-hand rule is, but no matter how much I search, can I find anything explaining why? What gives the directionality? And maybe Maxwell's equations explain it, and I need to go and look at them, but it feels to me like it speaks of some underlying asymmetry, which is baffling. Yeah, so do you know why?
Well, the first thing to say is, I absolutely do commend Maxwell's equations to you. However, Maxwell's equations are a description of the electromagnetic phenomena in the universe. They describe what happens in exquisite and beautiful detail. They don't really tell us why. It's important to realise they're a description of the physical universe as we discover it, as we measure it, as we see it playing out in front of us, whether that's on planet Earth or in space. But the fact is, magnetic field this way, if you're talking about electrons, then things go that way. If you're talking about positively charged particles, then it's reversed. So there's a lot of consistency about it, but you're right, it's not isotropic in any way. Maxwell's equations will give you a beautiful description. They're not really telling you why, but they are telling you about the nature of the physical universe.
Does anybody know?
I think why isn't really the question to consider. I mean, seriously, as physicists, we're measuring and we're saying how. We're trying to explain all sorts of different phenomena in the light of physical laws that we think we understand. Why is a bit of a different question. How is more the domain of physicists.
Hi, thank you for your talk. I was just wondering if we now have any ways of predicting solar activity and solar flares so that we can potentially schedule spacewalks so that they're not at the same time?
That's a most interesting thought, and I feel sure the astronauts of the world are very grateful for your concern. I mean, loosely, generally, you can say scheduling spacewalks for when we're at solar maximum, as we were in 2002, 2003, for example, when all those sunspots appeared on the surface of the sun, you are at greater risk then. When you're at solar minimum, you're at much less risk. But nonetheless, the appearance of sunspots and the ejection of solar flares is a little bit stochastic, and it does depend on the turbulent and the convective processes going on internally to the sun. So until we can probe internally to the sun, and I can't see that happening anytime soon, sadly I don't think we can make any detailed space weather forecasting of the kind that you have in mind.
The online audience is also a little worried about the astronauts, so there's one last question, if I may. Does the moon have a magnetic field? In other words, were the lunar astronauts subject to the full strength of the solar wind during the various Apollo missions?
I think they were. I mean, I think the moon has some kind of low-level residual magnetic field, but it's nothing compared with Earth's magnetic field.
Okay, well, thank you very much, and I hope you'll all join me in thanking the professor for a wonderful lecture.